This video provides qualitative results for our weakly supervised model on 3 tasks: video actor-action segmentation, video object segmentation, and action localization. Let's start by looking at how we generate pseudo annotation and make it evolve iteratively during the training stage. Here is an example. Given a video clip, we overlay the red actor-guided mask and the green action-guided mask on a sleek segmentation map to generate the initial pseudo annotation, which then enters the evolution loop from version 0 to version 3. Note that only annotations with a green circle are selected for training. Here we show more training samples involving scenes in a dim light or contain multiple actors. So what we can observe from this case is that pseudo annotations get improved by iterations. The false positive is gradually removed with a tighter contour close to the object boundary. Note that there are certain pseudo annotations that highlight background a lot. However, they are generally not selected. Hence, our segmentation network remains unaffected. Also, when there is a close shot, it takes some iterations for the pseudo annotation to figure out the full body. Once our model is well trained, we evaluate it on a test set. In A2D, only 3 frames in each video are annotated with pixel-wise ground truth, so we visualize the segmentation results in the following 2 ways. First, the snapshot presents the comparison between models and ground truth on the frames with official annotations. Our weakly supervised model are denoted as model V0 to 3 for different iterations. We also train another deep lab segmentation network under full supervision. The ground truth of the test frames is given in the last column. Second, we show the testing results on the whole video, technically running the segmentation network for each frame. It seems that our weakly supervised model soon warms up after 2 to 3 rounds of evolution and is quite robust even facing challenging cases like motion blur, multiple actors, occlusion, small-scale objects, or cases like background clutter. For instance, the sparrow camouflage in the bushes. Next, we exhibit the video object segmentation on the YouTube object dataset. Here we directly show the testing results for the video stream. Our model does inference on every frame, while the ground truth is updated every 10 frames. Our model achieves the state-of-art weakly supervised performance. More quantitative comparison with other competing models is available in the main paper. Finally, we extend our model to the task of weakly supervised action localization on the AV10. The goal is to validate that the proposed 3D-COM GCAM is able to capture the spatial temporal dynamics in the video by processing the video data in volume, which is in contrast to the 2D-COM GCAM that operates on a frame base. 10 action classes with evident person-to-person or person-to-object interaction are selected. Meanwhile, these classes also have a balanced amount of training data to train the 2 GCM models. In terms of the weakly supervised action localization tasks, we use an off-the-shelf person detector, and then assign the action label to the detected person closest to the GCM highlight area. It turns out that our proposed 3D GCM model is always more accurate than its 2D counterpart in pinpointing the region relevant to the engaged action, whether it is the hands of the person that serves something or a glass the person holds while drinking. Thank you for your attention.